Okay, so today's video is going to be about quantum mechanics. Change color, and quantum mechanics. Okay, so today, sorry. So we will be studying about the basics. This is topic that we'll talk about waves. Let's talk about waves first before we delve into the quantum mechanics of this. Okay, so we know that waves are definition of waves are is that wave is a mean of transferring energy via oscillations. While energy moves from one place to another, there is no movement of the particles. Let's suppose water. When water waves are moving, there's the particles are not moving, but actually the energy is being transferred from particle over to other particle. So transfer of energy, not the particle or matter itself. Okay, net resultant movement of particles is 0. Okay. Okay, so there are many types of waves, but the two main types of not many types. The waves, in what form waves can be, it is parallel, it's a what was the name of those waves again? The names were longitudinal, yeah, longitudinal, tudinal, and transverse. Okay, okay, so longitudinal waves are those waves which are parallel. Okay, they are parallel to the source, like the motion they are in, that motion is parallel to the vibrational source, parallel to vibration source. Okay, and the example could be a spring, that we could say a spring which can be stretched and not stretched, spring coil or whatever you want to say. And as per for the transverse wave, the wave direction is perpendicular. Okay, perpendicular. And mostly in quantum physics we talk about transverse wave, so it's measured as, is this how it looks like. Okay, this, the direction of motion is perpendicular to the source. Okay, and so let's now we know about the, and one more thing, photons or electromagnetic waves are transverse waves. And now let's talk about the properties of this wave that we are at it. This over here, this change in height is actually the amplitude. Okay, and then this is, if this full, we know that full wave is known as a lambda. This full wave is known as a lambda. half wave is known as lambda over 2, and this one is known as lambda over 4. This one is half 3 by 2, right? Or was it 1 by 2? 3 by 4. 3 by 4 lambda. And I think there are nodes as well. That's this antinode and nodes. I'm not sure about where the nodes, antinode nodes are, but yeah, there's also those as well. So just remember that water waves, sorry, not water waves, squashing and releasing a spring is longitudinal wave, and the particles or for electromagnetic waves moving is transverse wave. And one more key point is that we also have something known as compression and rarefaction. Rarefaction, where the particles are close to each other, that's known as compression, and where they have distance, a little like big distance, we call it rarefaction. Okay, now this was just a little bit overview of the types of waves, which are the longitudinal and transverse wave. We are going to like now let's get to the main thing of our topic, our like video, which is waves, of course, wave of quantum mechanics. Now if this is a sorry, if this is a wave, and we take wave, and when we talk about the phase of the wave, the phase or phase angle, we say that a phase is like after how many cycles the wave will restart. Means if this is a circle, we know this circle is 360 degrees. So we can say a wave, the phase of the wave as after this over here, this is 360. Okay, our phase can be written as the phase angle. Yeah, so phase angle or phase or wait, before doing this, let's talk about one more thing, that the angle. When we we draw this graph y and x, mostly we don't take y and x, so we'll leave it. So we take, if this is 360, this was 180, and this is 270, and this is 90. Okay, these are the angles. The x-axis represents the angle and y-axis represents some values. We will have to focus on those values. So if we have a circle, and like if we have the circle, okay, 1/4 of the circle over here, 1/4 of the circle represents 90-degree angle phase, because we know that 1/4 of a circle is a quarter of a circle, and it's always 90 degree, and this is in degree. In terms of radians, it's written as pi over 2, and 180, this is full, 90 plus 90 is 180 degree, and this is half, and which goes for pi, and so on till we get a whole circle 360, which will give us 2 pi. double of 180, and then so on 50, 540, 720. As it goes on increasing, the angle will increase and the radians will also increase depending on how many cycles we have. If we have one cycle, is 360 is the 360, we can also call this a period. Okay, and if it's like two cycle, it's 720, and as it goes on, we keep on expanding the phase. Okay, this is phase in degree and phase in, this is degree. Okay, and also we also take in account the wavelength. We already did this, that this one is known as 1/4 of a wave, this one is 1/2 of a wave, this is 3/4 of the wave lambda, and this is a full lambda. A full wave is known as lambda. And now let's talk about superposition of waves. Superposition of waves. How we have studied in quantum mechanics that superposition is nothing but is the particles being in more than one state at once, right? So now here we will talk about superposition of waves in two terms. One, constructive wave, and the other one is destructive wave. Okay, both give us superposition, but depending on what type of wave it is. So first of all, the first wave, which is constructive wave, is if we have two waves, okay, and they have the same they're moving in the same how do I say this? By the way, they're transverse wave again. Transverse wave. As we talk about quantum mechanics, we talk about transverse wave a lot. So, as they constructive mode, what happens is that their sides are both same. This one is also positive. This one is also positive. They're not different from each other. So, what happens is that when they combine, when they're so close to each other, what happens is that their height over here, this height will be increased. I'm sorry for the improper drawing, but this increase, what this will result is that the amplitude of the wave will expand. Amplitude, it will increased amplitude. Okay. So what we notice is that the waves, actually what happens to them is, if this is B and this is A, let's for example, this wave is A plus B. We are combining them, we are adding them together to get a more bigger or better wave. Now how is this related to quantum mechanics? Now here we have something known as wave function. This is what is related to wave function mostly, because when we are talking about particles in quantum mechanics, they don't have, when we don't measure them, they don't have precise location. Okay, and even though even though we measure them using the Schrödinger equation, we get the wave function of that position, get their properties using h d over dt. This is the Schrödinger equation. This is the Schrödinger equation, which can be used to get the properties. Schrödinger equation. Okay, now what we get by this is when we now when these waves combine, when we get higher amplitude, what we are actually getting is the chances of finding the particle over here is high. We're increasing our chances of finding the particle. Increasing chances of finding particle. Okay, but again they are QM. Okay, we are actually talking about superposition. So one more thing, when we explore these lines in terms of these lines, okay, what we call them is wave fronts. These are wave fronts. Okay, they are wave fronts. Just know that I'm not giving detail. the angle is always the same till they don't change the medium, and while they change the medium, their angle will of course shift to some other values. So if the wave, okay, when both meet at the same location, waves, a lift of, we are giving like some kind of a scenario like where we were talking about waves or something like that. So what happened that when they met at a certain point, what happened that their amplitude, since they were in the same phase, so their amplitude added and they gave a bigger wave. Now this was okay, that was a wave, this I think was a discrete wave. Now when we talk about continuous wave, we want over here one more thing, it can be constructive, destructive wave, or we can say constructive interference and destructive interference. Okay, because in mostly we use this thing in Young's modulus, sorry, not Young modulus, Young's double slit experiment, okay. Over here, okay, let's get straight to the topic of what the double slit experiment is, because then we'll talk about everything we know in double slit experiment with proper definitions. Okay, so let me sorry, let me just get what was it again? Let me just make the equation or the now let's get to the main thing of interference. We could also talk about one more topic, but that's not part of our deal or our stage, so we will not discuss it. We will only discuss the we'll discuss something known as diffraction grating. So when we were talking about waves, one more thing, when these waves pass through edges, or they pass through this certain gate or slit, they diffract. Okay, and again it will go on. Okay, this, and so over here we get a wave. That's what this wave is about. This wave is nothing but the probability, or the wave probability distribution of finding particle anywhere here, finding because we know that when we don't observe it, the particle spreads out and it's giving a pattern like this. So finding particle here, we can find particle here, finding particle probability. Particle prob. Okay, now that we have discussed this, we will be talking about one point which is very important, which is in quantum mechanics. When we have a light beam as wave, it goes through this slit. Okay, we can actually calculate, yeah, one more thing, these over here are known as orders. Okay, these are orders. The first one, and then 1 2 3 and 1 2 3, and this was center order, this was center order. Okay, now, and this is angle theta which it makes. So this pattern, actually what's happening is, what this theta, and then this gives sine theta. Let me write the equation first, then I'll describe what this equation does. Now this equation defines that a wave, a particle which goes through the slit, and the spots, the maximums we get, and like how many maximum we want to measure the angle between. Like if this is the second maximum, this is the theta. If this is the third maximum, this is the bigger theta, and so on. So, and d over here is the spacing between the slits, how much gap is between the slits, and n is a number of n can be recognized as n was what? I'm sorry, wait. N was yeah, n was what am I doing? N was this gratings, the order, and d is the numbers, the slit gap. Like we mostly say it as the number of lines per meter. We say grating space as number of lines per meter, and this is a sine theta, the angle which is made, and amplitude here. Amplitude is nothing but the amplitude of the wave. Okay, so how let's just wait. Now let's use one example. Let's just see one example. Oh, wait, one more thing. When we see the double slit experiment, what we see is that we have multiple points where there's light. So what we say is, these are known as maxima, and then these are these are called minimums, or these are dark spots. I think it's minimas, something like that. But the one which I'm the more important one, the colored ones, they're called maxima or maximum. Okay. So then let's use one example. In an experiment to examine the colors of light produced by hot helium gas, a chemist used a diffraction grating and found the first order maximum for each of three colors were, okay, we'll just do one angle. Okay, this is the grating D, and then this is the center one, this is the first grating. This is theta, and over here we have wavelength plus so this is n, theta and d. So n is first degree, because we know that it says over here clearly that it's found the first order maximum. We are finding the first order maximum, which is n. N is first order maximum. D here it says, they didn't specify D properly. They said if the grating he used had 1000 lines per millimeter. So what we do is that we convert that into D. How we do it is, if it's in millimeters, we say 1 times 10 to the power minus 3 over number per millimeter, which is 1000. Okay. How many were there? Or we will use the, we will not use this, we will not use this, sorry. We will use the values which are 1 over number of lines per meter. Okay, we will use this. Since our values were in millimeters, so we will convert it into millimeter and then we find our D. Okay, I will not solve it, I will just telling how to do it. I will be telling how to do, of course. This is we found D. Theta will be found. Theta is already given. Sometimes they give some. It depends on what we have to find, so it changes like that. So here the challenge is to find like the wavelength. So what we do is that we rearrange this equation. N wavelength is equal to sine theta n. So we just replace sine theta d. Sorry. But we replace it, so we get sine theta d over n is equal to lambda. This equation can be used to find lambda over here. Since we are given d, not given, we can calculate d. Theta is given, and the maximum or the number of orders, which order we are looking at, the first order from the center. Remember that when we take first, second, third order, we are saying we are comparing it to the center order. We say third order from the center. Second order from the center, fourth order from the center. So we are comparing with the second one. Orders are compared with the center order. Okay, and so even this can be written as, and one more thing you might have noticed over here, that as we are reaching the middle, the brightness increases. Okay, and as we go away it decreases. So we could take it as, okay, probabilities. That's how it is. Yeah, one more. Yeah, it was correct. That those which are the dark spots, they are known as minimas. Okay, so we are talking about slit. This is a double slit experiment, and so these are known as interference pattern, interference, where they match, they are interfering. And here what happens is that some over here it's happening is wave function collapses. Okay, wherever they're meeting, the wave function collapse, we get a definite value over there, a definite particle over there. Okay, and yeah, that's it. Thank you.